Welcome back. In this video, we will look at a very popular communication protocol known as the I2C serial protocol. So let's dive in. I2C, or I2C as it is also known, stands for Inter-Integrated Circuit, and it is a popular protocol for synchronous serial data transfer between multiple external devices. I2C was designed to take the best from both the UART and the SPI protocols. Like the UART, I2C requires only two lines to send and receive data, making the hardware setup simpler and more cost-effective. Like the SPI, the I2C also has a simpler software setup along with a simpler hardware setup and high data transfer rates. While I2C offers great flexibility in its ability to connect to multiple devices over the same two wires, it can be slower compared to the SPI and slightly more complex in large networks as compared to the UART. Some popular applications of I2C are sensors and actuators. Let's now look at how the I2C protocol operates. This can be broadly divided into 5 steps. In the diagram, the upper line is the serial data line, or the SDA, and the lower line is the serial clock line, or the SCL. Also, as you can see, the complete data packet is made up of two parts, the address frame and the data frame. The communication starts in step 1, when the controller leaves the SCL high and pulls SDA low, indicating to the peripherals that a data transfer is about to begin. In the second step, the controller sends the address of the device it wishes to communicate with in MSB mode, followed by a bit indicating whether it wants to read or write data. This address frame is 9 bits, with 7 bits for the address and the 8th bit for the read or write indication. A 1 denotes a read or receive operation, and a 0 on the bit indicates a write or send operation. In the third step, the targeted device acknowledges the communication by sending back an ACK signal, if the address was correct, or if it was able to parse the data, by sending a low signal or 0 on the ACK bit, which is the 9th bit. If it was unable to receive or parse, a high signal or 1 is sent on the data line. Note that the acknowledgement bit is sent for both the address and the data frame. With the acknowledgement done, in step 4, the actual data transfer happens. The data frame 2 is 9 bits with 8 bits for the actual data and the 9th bit for the acknowledgement. Once the data has been transmitted, in the final step, the controller sends a stop signal by pulling the SCL line high, followed by the SDA line, marking the end of the transmission. Finally, let's look at the wiring and see how two controllers can connect to two peripherals using I2C. As shown, both the SDA and SCL lines are shared among all the devices. Controllers and peripherals are wired in parallel, allowing seamless communication. Note that controllers communicate with the peripherals, but not directly with each other. Like before, also note that while each device on the I2C bus can either send or receive data, only the controller controls the clock, thereby establishing a clear controller-peripheral relationship among the devices. And that wraps up our overview of the different input-outputs and the serial protocols. With this knowledge, you should be able to read any datasheet with ease and choose the appropriate edge devices and peripherals for your application. In the next mini-section, we will look at the different sensors, understand how they work, and then explore some real-life scenarios where they could be used. It should be a fun section, and I am super excited. If you are too, take a quick break and then join me there. See you soon.